106 million people had their data stolen from a single bank in 2019. The strange part, the cloud provider did absolutely nothing wrong. Capital One ran on Amazon's cloud, and Amazon's half of the deal held up perfectly. The whole breach lived on the customer side of one invisible line. And one thing about that line trips up almost everyone, which I'm not giving away until we've drawn it.
Hey everyone, Erica here. That line has a name. CompTIA calls it the Cloud Responsibility Matrix, and the whole rule fits on a sticky note. The provider secures the cloud, and you secure what you put in it.
This is Objective 3.1, and the cloud is where people bleed the easiest points. Draw us the matrix, Erica.
Security of the cloud is everything Amazon owns. The buildings, the hardware, the whole network fabric, and the hypervisor under your machines. You never touch it, and you're never graded on it. Security in the cloud is your half. Your guest operating system and its patches, your data, and the permissions you hand out. Where that line sits depends on which service model you bought.
K here, and this is where I put a number on it because the model literally slides the line. Infrastructure as a service, a raw virtual machine, leaves the most on you. Platform as a service splits it. Software as a service hands you almost nothing to configure.
Read the grid the way the exam reads it. A check means you own it. Look at the bottom two rows. Your data and your identity are checked in every single column, no matter what you buy.
And here's the source in its own words. Amazon writes that the customer owns the configuration of the security group firewall. So a misconfigured, wide-open firewall rule isn't Amazon's breach. It's yours, in writing.
And that's the danger of the software as a service end. Almost nothing to configure feels like almost nothing to defend, and that's exactly where people get lazy and leave it wide open.
Right, and it's exactly how Capital One happened. Cynthia, what actually went wrong on their side of the line?
A web application firewall was misconfigured and tricked into a server-side request forgery. Let me show you the exact move in a lab, on a box I own, because seeing it ends the confusion for good. It fools the firewall into asking the cloud metadata service who this machine is. And the metadata service answers, no password required.
There it is, raw credentials, dumped to the terminal, and nobody typed a password. That's the moment Capital One turned into 106 million records.
That one address, 169.254, is the metadata service. It hands out the machine's role keys with no password because it assumes only the machine ever asks. The firewall flaw broke that assumption and the role was over-permissive, so those keys reached everything. The fix, a token-based metadata version and least privilege, is your job too.
Now contrast the cloud with on-premises because the same line idea carries over. On-prem, you own the whole stack. The building, the cabling, every patch. No shared line at all, which is total control and total burden. And it's the objective scalability trade-off in one image. The cloud grows on demand, while on-prem means buying servers you might never need.
Hybrid is where most real companies actually live, part on-prem and part cloud. The trap is that hybrid doesn't average your work. It stacks both lines, so you own your on-prem half and your cloud half at once. Add third-party vendors and it stacks again, because their breach becomes your breach through the door you opened them.
One more pairing, the objective list, centralized versus decentralized. Centralized is one brain making every call, easy to govern but a single point of failure. Decentralized spreads the load, resilient but harder to keep consistent. Kim, you've been sitting on the question every viewer types into search, so bring it in.
Yes, and it's the one that anchors this whole thing. If the cloud is so secure, why do most breaches still happen in the cloud? The honest answer is that almost all of them are the customer's half of the line, not the provider's.
That's the whole episode in one line, so hold on to it. Quick note before we move. We host the free Security Plus practice quizzes at certs.professorerica.com, so drill this objective there after the video. Now watch what happens when your half of the line gets written as actual code, because one bad line is about to clone itself 500 times.
So we stopped building servers by hand and started writing them as text. That's infrastructure as code, and it makes the security math faster and scarier at the same time.
Walk me through what hand building used to mean in plain terms.
An admin clicks through a console, opens a firewall here, sets a permission there. 6 months later, nobody remembers why a port is open. Infrastructure as code replaces all that clicking with one file you can read, review, and rebuild identically.
Repeatable is the word the exam wants. A security control stops being something one engineer remembered to click. It becomes a line in a file a reviewer can approve before it ever ships, and version control keeps the whole history.
Let me show you because a slide can't. This is a tiny Terraform file for a storage bucket. It doesn't list steps. It declares the end state you want, and the tool makes reality match it.
3 flags, all set to true, all blocking public access. The open bucket headline you read every other week is exactly these flags left at their loose default.
And I run it once. Watch the tool build both pieces and lock them the same way every time.
And here's the deeper win the exam rewards. Because the server lives in that file, you stop patching servers in place. You rebuild them clean from the file every time. That's immutable infrastructure, and it kills configuration drift.
Drift is the mystery server nobody dares touch. The one with a hand tweak from 2019 no one can explain. Rebuild from code means every server is identical and disposable. The phrase people use is cattle, not pets, but repeatable cuts both ways. Set one bad permission in a template you reuse 500 times, and you just ship the same hole 500 times instantly.
So the control and the catastrophe live in the same file. That's the honest trade-off. Kai, the other half of this objective, is serverless, and the name confuses everyone.
Serverless doesn't mean no server. It means you never see, own, or patch one. You hand the provider a function, it runs only when something triggers it, and you pay for the milliseconds. The operating system underneath is the provider's problem now.
Notice where that pushes the line from scene 1. Patching the host slides to the provider, a real win. But your code and its permissions stay yours, so an overprivileged function is still your breach waiting to happen.
And the shape of the attack changes with serverless. Your function is woken by events. An upload, a message, a queue. Every trigger is a new door, and a function running with too much permission turns a tiny trigger into a huge reach.
And serverless usually rides on microservices, the last term here. Instead of one giant app, you split it into many small independent services. The reason the book gives is blast radius.
Let me lay the two shapes side by side, because the security trade-off is the whole point.
So quantify it with a real shop. Picture Priya, a lead engineer whose team split one app into 50 microservices. She went from one front door to 50, plus every hallway between them. One big wall became 50 small locks, and every lock is now her team's job.
And here's the part candidates miss. All 50 services now talk to each other over the network, so every internal call needs authentication and encryption too. The pattern for that is a service mesh. Mutual authentication on the east-west traffic, not just the front door.
So the theme is already repeating. Every model that hands you speed hands you a new surface to defend. Hold that. The next pair, containers and virtual machines, is the one CompTIA turns into trick questions. Real quick, because this next part matters to you. If any of this is helping, tap that like button, then hit subscribe and ring the bell so the next one finds you. Both are free and take about a second, but they tell the algorithm to show this to one more person who needs it.
Containers versus virtual machines is the comparison this objective guarantees you'll see, and most guides teach it backwards. So let's do it the way that sticks, by watching one run.
Good, because I've explained this with the shipping container analogy for years and it never quite lands. Start us at the beginning.
Start with the old way, the virtual machine. A hypervisor carves one physical box into several virtual ones, and each runs a complete guest operating system. Its own kernel, its own boot, its own gigabytes. Strong isolation, but heavy and slow to start.
And virtualization is the foundation under all of it. One physical machine, sliced into many. A container just slices thinner.
Quick distinction the exam likes. A Type 1 hypervisor runs straight on the bare metal, the kind in a data center. A Type 2 runs on top of your regular operating system, the kind on your laptop. Bare metal is thinner and harder to attack.
Now the container. It doesn't bring its own operating system at all. It shares the host kernel and isolates only at the process level. Let me start 3 and watch the clock.
2 seconds. A full virtual machine wouldn't be at its login prompt yet. That gap is why the cloud runs on containers now.
Now list them and prove they share the host. Watch the last command.
That last line is the whole exam answer. One kernel shared by all 3 containers and the host. That density is why containers won. You fit far more per machine, and they start in seconds.
And that shared kernel is the catch, word for word from the literature. A VM escape has to beat the hypervisor to reach a neighbor. A container escape only has to beat the kernel it already shares, and then it owns every container on that host.
There's a second container risk the objective hides in plain sight. You don't build most containers, you pull them from a public registry. Pull a poison image and you invited the attacker in, no escape needed. Scan and pin your images.
And one risk that spans virtualization and cloud both: resource reuse. When a provider recycles memory or storage from one tenant to the next, leftover data can bleed through if it isn't wiped. In a shared cloud, isolation has to include cleaning up after yourself. Let me put the core trade-off on the board, because neither one is the answer.
So people ask which one is more secure, and that's the trick.
Neither. Wrong question.
Fair. Let me finish. Neither is the champion. The container wins speed and density, the virtual machine wins isolation strength, and the exam wants you to match the model to the workload.
Which is the constructive answer. Put your crown jewels behind the thicker boundary of a virtual machine and run your fast, disposable, scale-out work in containers.
Kai, you've been holding a question on this one. Go ahead.
The practical one every team hits. If a container escape can own the whole host, how do you run untrusted containers safely?
You stop trusting the shared kernel. You wrap the risky container in its own lightweight virtual machine, so an escape hits a hypervisor boundary instead of just the kernel. That's the best of both, and it's exactly where the industry landed.
One scaling note before we move. At real size, you don't run these by hand. An orchestrator like Kubernetes schedules thousands of containers, which makes the orchestrator's own interface the next crown jewel to lock down. But container, VM, or function, none of it is safe if the network around it is flat, which is where good people actually disagree.
Objective 3.1 also asks how we wire networks together, and 2 ideas sit at the extremes: a true air gap, total physical isolation, and logical segmentation, software dividing one shared network. Pick wrong and you either leave yourself exposed or you leave yourself unable to operate.
And the engine behind logical segmentation is software-defined networking, the term the exam wants. The rules become software you write instead of cables you run.
Here's the stake. Erica thinks the crown jewel systems belong physically off the network. Kay thinks software segmentation gets nearly all the safety without freezing the business. I'll keep them honest. Erica, make your case.
An air-gap system has no physical path to any other network. No cable, no wireless, nothing. For a nuclear control system or an offline certificate authority, that's the strongest control that exists, because an attacker on the internet simply has no road to it.
Hold on. Stuxnet crossed a perfect air gap.
It did, riding a USB drive carried in by hand. Which is my point. That's dramatically harder than a click from anywhere on Earth. The air gap didn't fail, it forced the single hardest attack path there is.
But that's exactly why it doesn't scale. An air gap that stops attackers also stops patches, monitoring, and updates. Air-gapped systems run years out of date because every fix is a manual trip with a laptop. You traded remote attackers for a blind, unpatchable box, and inability to patch is its own line on this exam.
Before you sell the alternative, Kai, let Erica answer that. Is an air gap even real once a technician plugs in to service it?
Honestly, not perfectly, no. Stuxnet proves an air gap is a control, not a magic wall. But for the rare system where absolute isolation matters more than staying current, it's still the correct tool. The mistake is reaching for it everywhere.
And that's my whole case. For the other 99%, software-defined networking carves one physical network into many isolated zones. A central policy called the control plane decides what may talk to what. You get isolation you can patch, monitor, and change in seconds instead of with a screwdriver. And you can fail it closed, so if the policy engine dies, the zones lock down instead of falling open.
Push back on that, Erica. Software dividing a shared wire sounds like one bug from the wall coming down.
It is exactly that risk. Segmentation is only as strong as the controller enforcing it. Misconfigure the policy or pop the software-defined networking controller and your neat zones collapse into one flat network. Physical isolation can't be misconfigured away. Software isolation can.
Granted, the controller becomes the new crown jewel, and you defend it like one. But I'll still take a zone I can watch and patch over a blind box I service by hand. The flat network breaches we keep teaching, like Target, were failures to segment at all, not failures of segmentation done well.
I'll grant you the default. For a normal enterprise, air gapping everything would freeze the business, so segmentation is the sensible starting point. I'm only holding the line for the handful of systems where isolation truly outranks every other need.
I can live with that split. Segment the many, air gap the sacred few.
Then here's the verdict the exam rewards, and it's the one the breach record backs up. These aren't rivals. Air gap the tiny set where total isolation beats every other need, the offline root authority, certain safety controls. Segment everything else and treat that controller as a top-tier asset. The trap answer picks one method for all cases. The right answer matches the isolation to what the system can actually tolerate losing. On February 5, 2021, an intruder reached the SCADA computer that runs a Florida city's drinking water and tried to raise a chemical to about 111 times its safe level. An operator watching his own screen caught it in seconds. This is the last family of models, the embedded and industrial gear, and it's where the stakes stop being abstract.
That family has 4 exam terms that travel together: industrial control systems and their SCADA, dashboards, the real-time operating systems running them, and the embedded computers baked into devices, plus the Internet of Things sprayed across everything.
Let me put a real control room up. Those screens are the human-machine interface, where one operator watches a whole plant. SCADA is the system gathering the data and pushing the commands, and it was never designed to face the internet. That's the original sin here. Decades-old operational technology bolted onto modern networks it was never built to touch.
Look at all those screens and switches. That's decades of equipment, a lot of it older than the laptop you're watching this on.
And this gear is everywhere people don't think to look. Power grids and factory floors. Hospital systems, the elevator in your building. Why is it so hard to secure?
Because this is the actual thing running the plant, and it wasn't built to be patched. Worth separating the two terms, an embedded system is a fixed-function computer baked into a device, while a real-time operating system is the software guaranteeing its split-second timing. You can't just reboot that for an update, and an embedded controller may have no patch process at all, running untouched for 20 years.
So inability to patch is the one consideration CompTIA leans on hardest for this gear. Say it back plainly, Erica, because it's the answer key.
When you cannot patch the thing, you don't harden the thing, you wrap it. And the Internet of Things is what makes that urgent, because Internet of Things multiplied the count into the millions.
Every camera, sensor, and smart bulb is a little computer with a default password and no update plan. That's the attack surface explosion this objective warns you about in one word.
So if you can't patch it, what do you actually do? I want someone who defends this gear for a living. Let me get our industrial systems expert on the line.
Glad to join you. The first thing I tell every team is to stop trying to harden the controller and start wrapping it. You assume the device can't be patched and can't defend itself, and you build the defense around it instead of inside it.
wrap it instead of harden it. So in practice, what does wrapping a controller look like?
In practice, it's the exact segmentation they just debated. The control network never touches the business network or the internet directly, and you monitor it heavily because if you can't patch the thing, your only warning is noticing when it acts strange. Oldsmar's save was a human noticing, not a control catching it.
The considerations list is long. In your words, which ones actually matter most for this gear?
Availability and resilience above almost everything. A water plant can't go down for a patch window. So high availability isn't a luxury, it's the design. You build it two ways, load balancing to spread the work across many nodes, and clustering so a standby takes over the instant one fails. Spread those across sites and you get geographic dispersion, so one flood or fire never takes the whole thing down.
And there's a sneaky one, risk transference. When you truly can't secure a system, buying cyber insurance to shift the financial hit is a real answer choice, not a cop-out, and CompTIA expects you to know it counts. The same list weighs cost, power, and compute too, because this gear often runs on tiny hardware that can't spare cycles for heavy security.
One closing reframe for the exam. When a question describes a system that controls something physical and can't be taken offline, the answer is almost never patch it. It's isolate it, monitor it, and build availability around it. Thanks for having me.
Perfect close, so carry this out of the whole objective. Every architecture model, from the cloud to a container to a water plant, hands you a new surface the moment it hands you speed or scale. Know which half of the responsibility line is yours, and you know the answer. Quick recap before we close. Every architecture model in Objective 3.1, from the cloud to a container to a water plant, draws a line between what someone else secures and what you secure. The model just decides where that line falls, and passing this domain is knowing exactly where it sits for each one.
The number I can't unhear is 106 million, from a breach where the provider did nothing wrong. That's the whole responsibility matrix in one story.
The first thing I'd check tonight is one storage bucket's public access setting in any cloud account you touch. That single checkbox is your half of the line made real.
And the one that flips the most answers: when a system controls something physical and can't be patched, you don't patch it. You isolate it, monitor it, and build high availability around it. When an exam choice says reboot to patch the water plant, that's the wrong answer by design.
Next time we wire the defenses themselves, firewalls, security zones, and the DMZ, placement that is a near guaranteed performance-based question. If you like the metadata trick, that one bypasses a firewall rule live.
If this made the responsibility matrix finally click, hit like and subscribe. We're building the whole Security Plus exam this way, one live demo at a time. And the free practice quizzes are waiting at certs.professorerica.com.
One we couldn't fully settle and we want it in the comments. Out of everything we covered today, which model surprised you most about where the responsibility line actually falls? The cloud, a container, or the water plant gear?
Every good teacher was once a confused student. Keep going.
Impressive work, Cynthia. I almost did not want to interrupt. This is Professor Erica. Thanks for watching and signing off.